Okay, so welcome to the first lecture for ELE 351. What we're going to talk about today is a little bit of an overview of what's going to be covered in the course. So we're going to start off and look at what's in Chapter 1 of Cedra and Smith. And in particular, we're going to talk about just sort of an overview of the sections that are in there, and then we'll delve into a little bit more detail about the amplifier section. So some of this will be a little bit of a review from circuits class. One of the things that I think is probably the most important memory you need to have from circuits is probably Thevenin and Norton equivalents and things that are related to that theory that you discussed in there. So what you ought to remember from Thevenin and Norton equivalent is you could have a Thevenin equivalent. We can call this voltage as a function of time, and a resistance here, Thevenin resistance R. Or we could talk about the Norton equivalent, which had a Norton current source, Is of t, and its Norton equivalent resistance, which is also R. The two are the same. And these are two different ways to represent a signal source. The book does have a little bit of specific, nature and how they write signals, and we'll talk a little bit about that. But one of the things that I want to point out here is just these are the two signal source types. One is obviously a voltage source, one is a current source. And we know that, if we want to relate the two, Is of t, we can translate the voltage source to a current source by just taking the voltage source and divide it by the resistance. If I want to be sort of specific, a lot of times we can call this R Thevenin and R Norton, and so when we find Is of t, we can say that's Vs of t over R Thevenin, but for the Thevenin equivalent and Norton equivalent, we know the two resistances must be the same. So that's sort of an important reminder about what you might get when you're doing Thevenin equivalent. And so one of the important topics that you can have here in relation to this is, remember, you can have some big circuit and I can tie this big circuit, which might have terminals A and B, just like either one of those two do. And whatever you have in that big circuit, it could have, independent voltage and current sources, it could have resistances, it could have dependent voltage and current sources, and you want to know what's going on at terminals A and B, you can always simplify this big circuit into one of or the other representation. So you can either do a Thevenin representation of it or a Norton representation of it. And so then when you attach some resistor, some load resistor between terminals A and B, rather than having to analyze the big circuit with RL attached to it, you can analyze the Thevenin or Norton equivalent and make things a whole lot easier. So there's some nice things that can be had from remembering these Thevenin and Norton equivalences. Okay, one of the things that you will often, not see is, remember, what if they want to know about a signal source and and they want to tell you, maybe I should say a signal source, and they talk about what's the Thevenin equivalent resistance of that signal source. Well, okay, one thing you can note is what is what's going to happen if we leave it open circuited? So we could look at V open circuit right here. This is a little strange kind of thing because we don't normally think about this in circuits quite this way. And what I mean by that is, what if we look at V open circuit? What is it? Well, I'll just go ahead and tell you that V open circuit is just Vs of t. But do you see it? The key is, if there's an open circuit here, what's this current? Well, that current is 0. If we have 0 current, then what's the voltage drop across this R Thevenin right there? Well, if the current is 0, that voltage drop is 0, and so if the voltage drop is 0, we can always, if I want to call this VR, we can always write an equation minus Vs of t plus VR plus VOC equals 0. And so that leaves us, if VR goes to 0, that leaves us with Vs is VOC. So that's exactly what I said. Also notice that we can get VOC from here too. If we have this open circuited right there, well, that V open circuit is IS times R Norton, which is the same as IS times R Thevenin. Well, what's IS? It's just Vs over R Thevenin, so that's equivalent to Vs over R Thevenin times R Thevenin. So this is just Vs. And I should point out, when I was talking about this is VOC up here. VOC is, so VOC is Vs. By the same token, if we look at something else that's also important, we can take, we normally think of the Norton equivalent when we're looking at it this way, but we don't have to just think about it like that. So let me draw this. And we also think of the short circuit current. Well, if I short out this, and I ask what the short circuit current is, well, by default, there's no resistance here, so is the current going to choose to go into that node and go down through the resistance or down through 0 resistance? Well, obviously it's going to all go this way, so this is all IS of t, and maybe I should have called that I short circuit there, but I short circuit is going to be IS of t. No current in our Norton branch. And of course, you could also figure this out up here. If I short the Thevenin equivalent, then the current's going to be Vs of t over R Thevenin. But what could Vs of t be written as? It can be written as Is of t times R Norton. R Thevenin and R Norton can cancel each other out, and so you get that I short circuit is equal to Is of t, just like we got before. So there's nothing any different about that. It will still work out the same way, but Is of t is equal to I short circuit. And remember, what's the Thevenin equivalent resistance? When we talked about it in circuits, R Thevenin is equal to R Norton, and it's equal to V open circuit divided by I short circuit. So if you find the open circuit voltage and you find the short circuit current, whatever circuit you have, you know the Thevenin equivalent resistance. So that's sort of a brief review, and something that will be pretty important for us as we go through circuits, or excuse me, electronics.